All right, so let's get started. The first thing I wanted to do is I just wanted to remind you that we have the midterm coming up on the 21st, so that's Monday. So I posted some information about the midterm over the weekend. And so if you haven't seen it, here it is. All it says is that the midterm will cover sections like chapters 1 and 2. And then up to separation of variables in Cartesian coordinates, which is a problem that we're going to finish today in the first 10 minutes or so. And then the stuff that we do beyond that will not be part of the midterm. What you can bring to the midterm is I will provide you with copies of the inside, front, and back covers of Griffiths. So those PDFs that you get, or those printouts that you get when you do the tutorial, you will also have those for the midterm. But you can also get your own piece of paper, like regular letter size, and you can write whatever you want on it, both sides. Okay, so that's what you can bring. And you can bring a calculator. My only restriction about calculators is that it can't connect to a network, go online. So graphing calculators are fine if you want to bring that. Honestly, it's unlikely that a calculator will be very helpful, but you can bring it in case there's some numbers that we have to punch in. All right. Also, I'm almost finished. I know it's been a long time. I'm almost finished marking assignment 1. And so my plan will be to bring those to the tutorial tomorrow, which I think it starts at 11, or I'll check it. And I'll bring those and you can pick them up there. Okay, yeah.
I've heard tomorrow is early to like a review.
Yeah.
Is it mandatory then? Like, I have some study to do.
Nope. So the tomorrow's tutorial is not like there's no quiz or anything like that. So yeah. All right, good. So then let us. I have here the notes that we wrote last time, and I just want to review them just to understand where we were, because we kind of left off in the middle of a problem. We started with this geometry where we had some conducting planes that were at a potential of 0 volts, that they were semi-infinite planes. So they covered everything along the x positive axis. And then there was this strip, this purple strip, which was another piece of conductor, but it wasn't electrically connected to the 2 semi-infinite planes. And on that strip, we could put some potential that changes with y. It depends on y. So it could be like, I don't know, a potential that increases linearly with y, or is completely constant, or whatever thing you can imagine. And we were going to try to solve this problem for the potential in the space between the semi-infinite planes. And we're going to do it by solving Laplace's equation. And the method we were going to adopt to solve Laplace's equation was to use separation of variables. And so for our problem, because of the symmetry, we don't expect the z-axis is coming out of the board here, out of the screen. So there's no z dependence to the potential. So we just wrote the potential as something that depends on x times another function that depends on y. And so in fact, there it is. And what we're going to have to do is we're going to have to solve Laplace's equation, and then we're going to have to match all of our boundary conditions. And if we can find some potential that satisfies Laplace's equation and the boundary conditions, then we know by the uniqueness theorem that that is the one and only solution. Okay, and there's no reason to expect, necessarily that this separation of variables is going to work for all problems. We're just trying to see what would happen. Okay, and so the first step was to put this product into Laplace's equation, and then we divided by x times y. That led to a sum of 2 terms, the first term involving only x and the other term involving only y, and they have to sum up to equal 0. The idea was this equation star has to be valid at all choices of x and y, And so the only way we can guarantee that is if the two terms separately were equal to the same constant, but one of them with a minus sign. And so we happen to choose to make the x term equal to c and the y term equal to minus c. Okay, and then we went and eventually what the separation of variables does for us is it separates our partial differential equation, Laplace's equation, into two ordinary differential equations, so equation 1 and 2. And we wrote down solutions for equation 1. So there it is. It's a sum of these two exponentials. And then we said, well, okay, and then we wrote down the solution for the second equation, which was sine and cosine. And then our total solution has to be the product of those two. All of that, none of this depended on the geometry of our problem, other than the fact that we said there would be no z dependence. Otherwise, this is completely general. We haven't imposed our boundary conditions, and that's the next step. We have to determine these constants. And so let's see, what did we do? One of our boundary conditions is that x goes to infinity, the potential has to go to 0. So that's because we're infinitely far away from that charged strip. Well, if we put in e to the k times infinity, that blows up. And so the only way to prevent that is to force a to be 0 all the time. Okay, so then that led to this kind of solution at the top. And then we looked at another boundary condition when y equals 0. We want the potential to be 0 because then we're sitting on one of our grounded plates. Okay, so we just put y equals 0. We ended up with like a sine of 0, which is 0, and then cos of 0, which is 1. But that doesn't work because I need this whole thing to equal 0. And so it's kind of nice. D prime is equal to 0. And so our solution gets simpler and simpler and simpler. Our third boundary condition is we have another conducting plane at y equals a. So the potential has to be 0 there. So wherever we see a y, we put an a, and that has to be 0. And that led to a condition on k, right? K times a has to be an integer multiple of pi in order to guarantee the potential is 0. And so there it is. And this is where we left off last time. And so what I want to do is I want to pick it up from there. All right. Now, what we could say about this is that so far, this does not satisfy all of our boundary conditions. We still have one more boundary condition to think about. Okay, so this solution does not currently satisfy all boundary conditions. The boundary conditions that it doesn't satisfy is, well, let's go look at it. Let's go way back here and look at our boundary conditions. Here we go. The one we haven't dealt with is when x equals 0, we need our potential to be v naught of y. And that's potentially something that depends on y. Okay, so we still have to consider that v when x equals 0 has to be equal to v naught, which could be some function of y. And you know, if I look at this, I see that I do have something that depends on y. It's a sine of n pi y. So the only possible way that this is going to be a solution is if somehow the potential on that strip has that sinusoidal dependence. But there's no reason to expect that it would. I could put whatever I want on that strip. So the trick is the following. Any linear combination of the, what do we have? E to the minus kx sine ky is also a solution to Laplace's equation. Okay, well, so maybe we can construct, let's see, v of xy is going to be some sum from n equals 1 to infinity of some coefficients en, well, and then a linear combination of our solutions. So the linear combination of what's in that box, so it's e to the minus kx sine ky. Okay, good. Well, what are we going to do with this? So we require then that v at 0, at x equals 0, times y has to be, well, okay, it's the sum. And then we have our bn. It's kind of nice, actually, right here, because k equals 0, this exponential is just going to be a 1. And then we have sine ky, and our boundary condition is that this is v naught of y. So this is our boundary condition. What does this look like? Does this remind you of something? Fourier series. Fourier series is great, right? Because I can take a bunch of sine functions of different frequencies and add them up, and I can construct whatever function I want as long as it lives on the same domain of the sine kx, right? So this is exactly a Fourier series. And what I can do is, I already know that this is going to be the answer, because you can give me any function of y you want, and I can find the coefficients bn that are going to match that function. And so let's see how that works. Okay, so we can select the coefficients bn such that v of 0y matches any v naught of y. Okay, so in order for us to go further, we actually are going to have to specify the functional form of v naught of y. And what we're going to do is we're going to choose it to be a constant just to see what it looks like. Okay, so to go further, we need to specify the form of v naught of y. So let's select, for simplicity, v naught of y is just equal to v naught, right? It's a constant. Okay, so does anyone remember what we have to do to find the bn coefficients? Yeah, we're going to integrate that v naught of y. What are we going to integrate? The product of v naught of y and what? Sine kx. Yeah, that's right. So just like for the Fourier series, bn is found by evaluating, let's see, at bn is equal to 2 over a, the integral from 0 to a. So that's the range of y. Y, we have our conducting sheets, one at y equals 0 and one at y equals a. So that's the extent of the little strip on the end. So v naught of y times sine, and our k was n pi over a. And then we multiply by y and dy. But what we said is we're gonna make this now just a constant. And that's a nice choice, because then we're just gonna integrate sine. I can do that. I can pull that one off. Okay, so this is gonna be 2v0 over a, the integral from 0 to a of sine n pi a over y dy. Okay, so the sine becomes minus cos, I think. So we're going to pick up a minus sign. And then we're going to get a factor of a over n pi. And then we're going to have cos of n pi a y. And then we have to evaluate this from 0 to a. So hopefully that's right. Let's see what happens. Okay, so this is going to be what? The a's will cancel. And so we get our bn is equal to minus 2v0 over n pi cos of, so if I put in a, I'm going to get n pi minus the cos of 0, which is 1. Okay, so if n equals 1, cos of pi is minus 1. If n equals 2, cos of 2 pi is plus 1. And this is going to alternate between plus or minus 1. And what I could do is I could just say this is like minus 1 to the power n. So it'll be even for n even, it'll be plus 1 for n even and odd, minus for n odd, which I think is what we want. And so our bn is equal to minus 2v0 over n pi minus 1 to the n minus 1. But what does bn come out to be if n is even? Just put in a 2, what am I going to get? 0, right? So bn is going to be 0 for n even, and bn is going to be equal to 4v0 over n pi for n odd. We get a 4 because if n is odd. I'm going to get minus 1, which is minus 2. Minus 2 times minus 2 is plus 4. V0 over n pi. So the potential, the solution, the final solution for v of x, y is, okay, v of x, y is going to be equal to, we said we had to sum over n, but now our sum is restricted to odd values of n. So this is going to be like a sum of 1, 3, 5, 7, and so on. And we had a 4v0 over n pi. Those are our bn coefficients. Remember, we had this exponential in here. There it is. E to the minus kx. It was temporarily gone because we were doing the boundary condition of x equals 0. But in general, we have e to the minus kx, and k was n pi over a. And then we had the sine of ky. Again, it's n pi over a for k, and then we have our y. And that is our solution to our problem by separation of variables. Had we gone through all this procedure and not uncovered the Fourier series, for example, and we just found that we couldn't just satisfy, there's no way to satisfy all the boundary conditions, then separation of variables just would not be a solution. But as it turns out, we could do it. All right, good. So that's the end of our separation of variables in Cartesian coordinates. So what we want to do next is start thinking about, what if we had a problem in spherical coordinates? We could still do separation of variables. Instead of x of x times y of y times, in general, z of z. We would have an r of r times theta of theta times a phi of phi. And we're going to do all of that. And when we do that, we're going to run into a differential equation whose solution gives the so-called Legendre polynomials. Have you seen Legendre polynomials? Where did you see them?
304.
304. So Jurassic is doing it for hydrogen atom?
No, well, maybe eventually, I
Yes.
there's something that saw me pop up and I went and looked at them like, holy smokes.
Oh, okay, good. Legendre polynomials are great. Okay. I'm a little uncomfortable with the idea of just saying, look, these are the solution to some differential equation. There's mysterious polynomials that, I don't understand and I have to look them up when I need them. I'd rather tell you something about them. It's a bit of a detour, but I think it's going to be worth it. Okay, so let's try. For now, we're not doing an E&M problem. I'm just telling you about some properties of some polynomials. Okay, so we're going to do Legendre polynomials. And I'm going to tell you about some of their fun facts. They're labeled PL of X. And so you get different polynomials for different values of L. L is some integer, 1, 2, 3, 4. Okay. I'll say right off the bat that we will be interested in the region -1 to +1. Okay. The first thing I'm going to do is I'm just going to write down the first few polynomials. And then we'll start figuring out some of their properties. All right, so I'm going to construct this table here. And we'll start with, I need polynomials. My polynomials are going to get bigger, so I need to give myself a bit of space. Let's move you over here. Okay, so we'll start with L. In fact, L can be 0. When L is 0, the first Legendre polynomial is just a 1. Okay, and 1 is an even function. And so if I evaluate 1 at any value of x, I always get 1. Right, so that one is not so interesting. Then we go to L equals 1. And the next Legendre polynomial is x. X is an odd function. If I sub in for p of x, x equals 1, and I compare, I'll get 1. Okay, and so it's 1. If I sub in x equals -1, I'll get a -1 on the boundary of our range that we're interested in. Okay, the next one is L equals 2. Here we have a polynomial 3x squared minus 1. So let's look at this. X squared is an even function. And then we have a -1, a constant. Constants are even functions. And so this is an even function. Okay. What happens if I put in x equals 1? I get 3 minus 1 is 2 divided by 2. I get +1. What if I put in -1? I get -3 minus 2. Sorry, -3 minus 1 is -4. No, I'm wrong again. X squared. So -1 squared is +1. 3 minus 1 is +2 divided by 2. I get +1. All right. Let's do a couple more. L equals 3. We're going to get a 1/2 5x cubed minus 3x. There's kind of a pattern emerging here, right? The even values of L have only even powers of x. And the odd values of L have only odd powers of x. And so that pattern is going to continue, and we're guaranteed to find that the Legendre polynomial is an even function if L is even, and it's an odd function if L is odd. Okay, so fair enough. If I put in x equals 1, 5 minus 3 is 2 divided by 2, get 1. If I put in a -1, I'm gonna get -5 plus 3 is -2 divided by 2, it's -1. There's another pattern emerging. Whether L is odd or even, the Legendre polynomial at the boundary x equals +1 is always 1. And the Legendre polynomial at the other boundary, x is -1, alternates between plus and -1. It's -1 for odd L, and it's +1 for even L. Okay, that's kind of nice because the domain where our functions live now are between x is plus or -1 and y is plus or minus. So they live in this box, okay, of area 4. Okay, fair enough. Let's go to L equals 4, just to be complete. It's going to be 1/8 of 35. It should be only even powers of x. So there it is. This is an even function. I won't bother checking. You can check if you want, but they're going to boundaries at the boundaries is always going to be +1. And we'll do this will be the last one I write down. You can see they're getting more complicated, but the fact that they are just either odd powers of x or even powers of x, that will always be preserved. 1 - 1. Okay, and then we could just keep going. I'm going to plot some of these for you, but I'm not going to try to draw them. I'm going to try to find the figure that I already have. And I'm pretty sure it's right here. Let's copy this thing. Copy. That's not what I wanted to do. Copy. Okay. Let's see if we can stick it in there. Where did our notes go? Which ones are we working on? Nope. Sorry, it'll take me, that's 331. What was the date? Oh, here it is. Good. Okay, let's paste this in. There they are. Nice. So I said they live on this box, so they go from -1 to +1 and -1 to +1. The P0 is that constant blue line at the top. Here's P1 is this linear orange line. P2 is the green quadratic, and they get more and more complicated as you go on. Notice one thing. One thing I want you to notice is, besides the fact that the endpoints are always at +or -1 or +1 when x equals +1, as we increase L, we get more wiggles between -1 and +1. Sine does the same thing, right? If I plot sine of x, you know, I can have it at 1 hump between a 1 period, or I can increase the frequency and get 2 oscillations, or 3 or 4 or whatever. So these, in some sense, have something in common with the sine functions, is that we get more wiggle as we increase n. Here, where's the brown one? The brown one is L equals 5. That's the biggest one we have. That's the one with the most wiggles. If I added more higher values of L, you'd get more wiggles. Okay, fair enough. So what else could we say about these polynomials? So Legendre polynomials arise as solutions to the following differential equation. I'm going to show you another way we can get them as well. Okay, this differential equation is not nice looking. It's 1 minus x squared d2y of x dx2 minus 2x dy of x dx is equal to minus L plus 1 y of x. And we're going to call this equation something. We're going to call this number sign. So this seems arbitrary. I just wrote down some random differential equation, but when we go try to solve Laplace's equation, del squared v is equal to 0, and we use spherical coordinates and we use separation of variables, we're going to run into this equation. You know, it won't be obvious at first, it'll be in disguise, but we'll be able to show that they are the same. And, you know, when you're doing your hydrogen atom problem, you're going to do a separation of variables technique, and everything is exactly the same as what we're going to do. You're going to run into this thing as well. And so that's why you're going to see the Legendre polynomials in these cases. It's whenever you're trying to solve like a del squared v type problem using separation of variables in spherical coordinates. Okay, so what do we have to say? L is some integer. All right. Okay, and we are interested in the domain -1 to +1 for x. Okay, so maybe I'll just make a comment. This seems arbitrary, but we will encounter number sign when solving del squared v is equal to 0 in spherical coordinates. Using separation of variables. Okay, you also see it in quantum mechanics. All right, let's just confirm that the first few polynomials actually do solve this differential equation. So let's consider the L equals 0 case of number sign. Well, that one's pretty easy, because if I put L equals 0, the right-hand side is going to be 0. So then what we're left with is 1 minus x squared d2y dx2 minus 2x dy dx is equal to 0. And you can just, in your head, if I put in y is equal to 1, then these two derivatives vanish and we get 0 equals 0. Okay, so y equals 1 is a solution. And in fact, y is going to be the 0th Legendre polynomial. All right, so let's do the case L equals 1. The left-hand side is always the same. It doesn't have any L's. So as I change L, nothing happens to the left. It's only on the right where we'll see it change. And it was, I think it was minus L times L plus 1. So L is 1. So it's 1 times 2. So we get it 2. And then there was a y sitting over there. All right, this one we can kind of do in our head as well. Let's try y equals x. Okay, two derivatives of x is going to be 0. So that's gone. Let's see, we could do 2 times x dy dx. So this is going to be dx is just 1. So we're going to get a minus 2x. But y is equal to x. So we have minus 2x is equal to minus 2x. So y equals x is a solution. And in fact, y is equal to the first Legendre polynomial in this case. I'm going to do one more just to show you that it works. All right, so we get 1 minus x squared d2y dx2 minus 2x dy dx is equal to minus. So it's L times L plus 1, and L is 2. So it's 2 times 3 is 6y. It's no longer obvious, at least not for me, what the solution is going to be. So the solution is not obvious. And so what we'll do is we'll try setting y equal to P2. of x, and P2 of x was 1/2 3x squared minus 1, I think, if you go look at our table. Okay, so we're going to need stuff like dy dx. And so what's that going to be? That's, I think, just going to be 3x. Okay, and then d2y dx2. Take an x derivative of this, we just get a 3. All right, so then we're going to get what? 1 minus x squared. The second derivative is just a 3 minus 2x times the first derivative, which is 3x, is equal to minus 6 times y. But for y, we've chosen the second Legendre polynomial, or the L equals 2 polynomial. All right, and let's see what we have. We have a 3 minus 3x squared minus 6x squared is equal to, okay, so 6 divided by 2 is 3, so 3 times 3 is 9x squared, and there's a minus sign, minus 9x squared, and then we get plus 3. So the 3's are going to cancel, and these will cancel. Okay, and so that's all right. The solution is y is P2 of x, which is this 1/2 of 3x squared minus 1. All right. Anyways, it seems like, you know, at least for the ones that we've tried, we can verify that they are solutions to that differential equation. There's a nice way to generate these polynomials. So the Legendre polynomials can be generated using the so-called Rodriguez formula. And what that looks like is PL of x is equal to, it's not that bad. There's some prefactor. It's 2 to the power L times L factorial in the denominator. And then it's the L derivative of x squared minus 1 to the n. Okay. So let's just try P0. Well, 2 to the 0 is 1, 0 factorial is 1, 0 derivatives of x squared minus 1. Okay, so we'll take no derivatives of that, so we just get x squared minus 1 to the power, oh, that should be an L, sorry. This should be an L to the power L. Well, L is 0, so anything raised to 0 is 1, and so we just get a 1. Okay, so that's good. P1 is equal to, like, okay, 1 over 2. Oh, look, that's our 1/2 already. Sorry, no, that's going to go away. I'm getting better. So this is 2 to the 1 times 1 factorial, and then it's 1 derivative of x squared minus 1. And so that's 1/2 times 2x, and it's x. Okay, we'll do one more just to verify that it works. So this would be 1 over 4 times 2. So L equals 2. So we get 2 to the power 2 is 4. 2 factorial is just 2. And then we have to take 2 derivatives of x squared minus 1 squared. Okay, so we could do this 2 ways. We could either expand this out, or we could do some chain rule. So it's going to be 1 over 8 d by dx of, let's do chain rule, 2x squared minus 1, and then we have to multiply by the inside derivative, is 2x. So I think this is, let's see, 4 divided by 8, so we'll get a 1/2 d by dx of, what do we have? X cubed minus x, I think, if I've done this right. So we would get 1/2 of 3x squared minus 1. There it is. So there's the second polynomial. And you could do this, you could keep going, and you could find more and more of these polynomials. You'll just regenerate a table that we wrote down at the beginning. Okay. So now is where I want to go on a bit of a detour. Okay. So, and it'll be a long detour, but I think it's going to be worth it. We'll see. You could tell me later whether it was worth it. So I'm going to start by, let's consider sine pi x and sine of 2 pi x. So what we'll do is we'll plot these functions. I'm going to plot them on the interval x is -1 to +1. Okay, so here's x. So what we'll do is we'll say, all right, we'll plot sine of pi x. So what do I know about sine pi x? When x equals 0, that has to be equal to 0. So there'll be a point here. When x is equal to 1, we'll get sine of pi, and that would have to be 0 as well. When x equals -1, we would have sine of minus pi, and that also has to be 0. How many is 1, 2, 3, 4, 5, 6? 1, 2, 3, 5, 6. So that's out here somewhere. All right. And then you go, well, what if x is a half? We'll get sine of pi by 2. Well, that's going to be +1. So half is somewhere around here. And then -1/2 is going to be somewhere around here. Okay, and then so of course, I mean, we all know what the sine function looks like. So I'm going to draw the sine function here, and it looks something like this, right? Should be a little more rounded over here, I suppose. Okay, and so this is sine of pi x, and we can label on this plot here. This is +1/2, this is 1, this is 0, this is -1/2, and this is -1. All right. And so now we're going to do the same thing for sine 2 pi x, and we'll make that one blue. Well, okay, there is a point at 0, of course, and there's a point 0 at ±1. But let's try a half now. If I put in half for x, I get sine of 2 pi times a half with sine of pi. Well, that's 0. And I'll get a 0 over here as well. In fact, the peaks and minima will be at these subintervals of -1/4, -3/4, +1/4, and +3/4. Okay, so if I put in a quarter, I'll get sine of pi over 2. So I'll get a +1, and that'll sit here. And then I'll get a -1 at 3/4. I'll get a -1 at -1/4, and I'll get a +1 at 3/4. Okay, and so I'm going to try to draw this sine of 2 pi times x, like so. Okay, we're doing this for a reason that hopefully will become apparent. All right, there we go. So what I want to do with this picture is I want to think about these functions as vectors if I can. And the reason is that I know a lot about how to handle, say, vectors in 3D. If I had a vector A and B, if I take their dot product, what I'm really asking is, like, how well aligned are those two vectors? If they're parallel, I'll get a large dot product. If they are perpendicular, I'll get 0. So we're going to try to do something similar for functions, and I want to make this analogy with vectors and dot products. Okay, so I'm going to leave a bit of space, and what I'm going to say is we're going to try to think about functions f of x as vectors with components. And so how are we going to do that? Well, what we're going to do is we're going to discretize our functions, or we're going to sample our functions at evenly spaced intervals of delta x. So do this by sampling functions at an evenly spaced interval delta x. Okay, so what does that look like? Well, we go back here and we say, all right, what I'm going to do is I'm going to sample, start with the red one. I'm going to add some points here so that I get finer resolution in my sampling of my sine function, sine pi x in this case. Okay, so what I'm going to do is I'm going to call this sample f1, this sample is f2, this sample is f3, and so on. And so f3, for example, is f of x evaluated at whatever x this is, happens to be minus 3/4. Okay, and what we have here is our delta x is how far we move along the x-axis between samples. So if our domain is from 1 to -1, and we take n samples, delta x will be 2 divided by n. So delta x in general will be the size of the domain from B to A divided by n, the number of samples. So A to B is our domain, and n is our number of samples. Okay, so then I start constructing my f vector. And so that's going to be, well, f1 and f2. It's going to have all these components, and it's going to go up to fn. Just like if I had a vector A in three-dimensional space, I could write that vector as a column matrix where I have my x component, y component, z component. Just now I have n components. That's the difference. And then we go through, and then we're going to do the same thing for the blue function. And I'm going to call this function g. Okay, so here is g1, here's g2, here's g3, sampled at the same intervals. So my vector g will be g1, g2, g3 to gn. Okay. So the components of the vectors are given by, well, okay, f1 is f1, sorry, f at x1, f2 is f at x2, and so on. Same thing for g. Okay, so what the goal is going to be is we want to construct something similar to a dot product, but for functions. So let's just think about dot product. If we have some 3D vectors, what I could do is I could say, well, that vector is going to have an x, a y, and a z component. And if I had another vector, it has its own x, y, and z components. So then, I mean, we know how to do this dot product. One way to write the dot product in matrix notation is to take a row matrix and then multiply it by column matrix. So you take the transpose of one of the vectors and then multiply it by the other. Okay, and then this obviously just leads to the sum of vi ui, where I is going to be x, y, or z. Okay. There's nothing stopping me from doing that for our discretized function vectors. So let's do this. This is called, have you seen like inner products somewhere? So we're doing inner products, right? But I want to be pretty strict about our analogy with normal vectors. So the analogous inner product for functions might be something like, well, what if I just took f1 times f2 times, or sorry, f1, f2, f3 as a row, and then multiplied this by g1, g2, g3 as a column? Well, that's just going to result in fi gi for I equals 1 to n. This is not going to be exactly our definition of the inner product, but we'll see what changes we need to make. So therefore, our inner product is going to be, let's make some notation for our inner product. We'll have our vector f and our vector g, and we'll use these angle brackets for an inner product. We've got a comma in there. And so that's going to be the sum from I equals 1 to n of, well, what did we say the components were going to be? The components were going to be f evaluated at the particular value of x, and same for g. Does anyone see a problem with this? What's gonna go wrong here? What would happen if I doubled the value of n? Yeah, I mean, I'm gonna double the number of terms of my son, and let's imagine that I had two functions that were always positive. Then if I multiply these two, I'm always going to get positive numbers, and I'm just going to add up more and more positive numbers. Things are just going to blow up as I increase n. Okay, so a problem with this definition of inner product is that as n is increased, let's say as n increases, the value of the sum is not stable. Right, in math, that's what they do when they look at a series and say, does it converge or not? They look at partial sums, and so you sum up to some n, and you should be approaching some stable value as n gets larger and larger and larger. If that happens, you'd say you have a converging series. This does not have that property, so we need to fix it. And so let's go back and look at this picture here. And if I increase n, it's just like putting more points in here, and so obviously the sum is going to have more terms in it. So I want to come up with something that's not going to depend on how big I make n. And one thing I can do is, I can take this point-by-point product of the functions, and then I can find the area under the curve. If I find the area, all I have to do is do the point-by-point product and then multiply by delta x. That's kind of nice because delta x was constructed from the domain of our functions, -1 to 1 in this picture, and the number of sampling points. So as I increase n, the number of terms in my sum goes up, but delta x gets smaller by the same proportion, and we should end up with a stable value for this inner product. So we fix this issue by multiplying multiplying by delta x is b minus a over n. But I'm just going to write it as delta x. And so we would say this doesn't quite work. And so we'll redefine our inner product in this way. Whoops, this is G. And then you know what's going to happen. We are going to take the limit that delta x goes to 0, and that will be our definition of the inner product. In the limit that delta x goes to 0, our inner product for functions is the integral of f of x, g of x, dx on whatever our domain is. Now, because we've built this up, starting from an idea of dot products, we should interpret the result of this calculation as being similar to the results for dot products. Dot products, if two vectors are sort of aligned, pretty closely aligned, we get a large result. If they are perpendicular, we get 0. So what this inner product actually evaluates for us is how similar are, how aligned or how similar are the functions f and g. If they're very similar, we should get a large answer. If they're very different, we should get 0. So if f of x and g of x are similar, we should find that this inner product fg is large. Well, maybe I'll just leave it at that. Well, okay, if f and g are very different, it's small or 0. Let's see what would happen if we tried to do this for this function. Are these pair of functions, right? Suppose that we have the red curve is our f and our blue curve is g. That's how we labeled it already. Well, let's think about this. There's going to be some special lines or special values of x here, and we've already got them kind of delineated. If I'm from -1 to -0.5, what is this point-by-point product going to be? Is it going to give us negative or positive values? Right, so we got red values are negative, blue ones are positive. We multiply them, it's going to be negative. So we're going to get a bunch of negative values. And so I'll make the negative values red. So these are, oh, hold on. Let's be careful. Let's not go outside of our domain. There it is. Okay, so now what we can do is let's do our shading. Okay, good. There's another section that's going to be negative. Which the other one's going to always be negative? It's this one, right? Here we have negative values of g and positive values of f. And when we do that point-by-point multiplication, we're going to get negative results. And then everywhere else, we'll get positive results. Here we have positive numbers times positive, and here we have negative times negative. All right. So everything else is going to be negative. And so what's the total going to be for this inner product? Looks like it's going to be 0. Damn well right, it's 0. Okay. So it's because these are negative by the same amount that these are positive. Or sorry, this product is negative by the same amount that this one's positive. So when we calculate the area, we'll get 0. What do we say about functions, or sorry, vectors that have 0 dot product? They're orthogonal. So these two functions are said to be orthogonal. They're as different as they can be. Okay, so for f is equal to sine, what did we have? Pi x, and g is equal to sine 2 pi x. The inner product, fg, how are we doing time-wise here? Oh, not bad, is equal to 0, and we would say f and g are orthogonal. Okay, good. I want to see if we can generalize this argument for the sine function. Let's check something that's a little more general. Let's check -1 to 1 of sine m pi x times sine of n pi x dx. So this will be our f of x, and this is going to be our g of x. And the only restriction is that n and m are integers, and m is not equal to n. Okay, what do you think the result of this inner product is going to be? It's going to be 0, right? If you have done Fourier series recently, this is critical for Fourier series. So this is f of x, g of x. Now there's a couple ways that you could think about this. We're on a interval that is symmetric, and sine is an odd function, and we multiply it by another odd function. So this product is even, and an even function integrated over a symmetric interval is 0. Okay, so this is going to be equal to 0 for all n m with n not equal to m. And so what you can say then is that the set of functions sine n pi x is a set of orthogonal functions. So they're all going to be orthogonal to one another. So sine n pi x defines a set of orthogonal functions. Yeah, and maybe I'll stop there. Okay, so let's see if we can kind of come back to our vector analogy. Let's just think of Cartesian coordinates, x, y, and maybe z, or something like that. Maybe I should have said x, y, z. X, y, z are, we could call them like a basis set of vectors for our 3D space. And what I can do is I can write any other vector in terms of components along x, y, and z. We're going to do the same thing for functions. If I have an orthogonal set of functions, then on that domain, I can write any other function as in terms of components of all of these basis vectors, where n is going to be 1, 2, 3, 4, and so on. Okay, and so that's what I want to write down. So let's consider a 3D vector space. A set of orthogonal vectors in that space are, well, x hat, y hat, z hat. And what that means is it is possible to construct any vector v in that space in terms of components along x hat, y hat, z hat. Okay, so what does that look like? You know, at the risk of being too slow here, let me just write this down because I want to show you another way of expressing the same thing, right? This is just obviously a 3D vector with 3 components. V sub x is the x component. How could I find that? Well, what I could take is take my vector v and take a dot product with x hat, and this is vx. So another way of writing this vector is as constructing the coefficients as dot products and then multiplying by the basis vectors. Okay, I want to do the same thing for my function space. Okay, so in a similar way, we can write any function f of x in terms of, I'll put in brackets, components aligned with the orthogonal basis functions, sine, how did I write it? N pi x. And what I'm going to do is I'm going to try to write down an expression for functions that just follows exactly this sort of format. Okay, so what's it going to be? So my f of x will be, let's see, dot product with a basis vector. Okay, so I'm going to switch that to an inner product. And then my basis vector, my first one is, say, sine n equals 1. So pi x. So I evaluate that inner product and then I multiply by the basis vector. Okay, and then to get the next one, what I'm going to do is I'm going to take my function, multiply it by the next member of the basis. That would be n equals 2. And then sine 2 pi x. I'll write down one more. 3 pi x sine of 3 pi x, and plus so on. All right, I could maybe write this a little bit nicer. I could say, well, let me call the coefficients, I'm going to call them Bn, and I'm going to set those just to be the inner products. And so in general, it would be n pi x. But if we write down what the inner product actually is, it's the integral over the domain of f of x sine n pi x dx. This is the goddamn thing we just used to solve the first problem, right? So we just re-derived Fourier series using this analogy with linear algebra applied to our functions. Okay, so that means then f of x in general is written as the sum of n equals 1 to infinity of bn sine of n pi x, where the bn's are given by these inner products. But really what's happening is the inner product is just saying how similar is f to this function, or what's the projection of my function onto that component of my basis. All right, so that's pretty neat. I like that. I like it a lot. So why are we doing this? Well, the reason we're doing this is because just like we live in our 3D space and we say, you know, when I'm talking about blocks sliding down planes, I like to use my Cartesian coordinates, x hat, y hat, z hat. But I'm stuck here in Phys 301 and I'm asked to solve problems about charged spheres. And I like working in spherical coordinates better. It's way more convenient. I could always do things in Cartesian coordinates, but it would be painful. So there is other bases or other bases that are possible, right? I could use r hat, theta hat, phi hat, or I could use cylindrical coordinates. Same thing's true for functions. I don't have to express this series expansion of f in terms of the set of orthogonal sine functions. Maybe I can find another set of orthogonal functions. What do you suppose one possible set is? What did we start talking about? We talked about Legendre polynomials, right? Legendre polynomials is another set of orthogonal functions. Okay, so what I want to do, 5 minutes. Okay, we won't do this today, but I will just make a note that Legendre polynomials are another set of orthogonal functions.
Could they exist in different function space then?
The way I did this construction is I happened to choose my domain for the signs to match the domain for the Legendre polynomial. So any function that I could write on -1 to +1 in terms of sign, I can also write in terms of. Yeah. So how would that work? Well, I would say f of x is equal to the component along the first Legendre polynomial. So it's going to be f of x inner product with p0 of x times p0 of x plus the inner product of f of x with p1 of x times p1 of x plus and so on, right? And so in general, this would be so let's say I call this Cn this time. Well, this would be C0, this would be C1, and so we would eventually get to f of x times p. I should use L, shouldn't I? Let's use L, not N. PL of x. And so this, we'll call this CL. And so then f of x is going to be equal to the sum from L equals 0 to infinity of CL PL of x, where CL is given by the integral from -1 to +1 of f of x times PL of x dx. So what we haven't done, and I think what I would like to do next time, is to show you how you could actually construct a set of orthogonal functions. And I want to show you that we recover the Legendre polynomials. Have you seen this thing called the Gram-Schmidt method? Good. So then I will introduce that to you. It won't be Monday, it'll be Wednesday of next week. Yeah.
Yeah, basically because both the Legendre polynomials and the sine are orthogonal bases.
Yeah.
Can you, I guess with the Gram-Schmidt, just produce some transformation from sine to?
Yeah, we're gonna write down a little bit of a method to figure out how to do this. Let's see if we can prove that these functions are orthogonal. Let's do the easy one first. Let's check if P1 is orthogonal to P0. So P1 is this linear one, P0 is the constant. So if I multiply them point by point, I'm going to get a bunch of negative numbers from -1 to 0. I'll get a bunch of positives from 0 to +1, and I'll add them up and I'll get 0. So those are definitely orthogonal. What about the quadratic and this one? Well, it's the same thing, because this linear function is half the time negative, half the time positive, and the green function is symmetric, that's guaranteed to be zero. In fact, I guess you could always say the integral of an even polynomial times an odd one will produce an odd function, and that is guaranteed to be orthogonal. So anything with a even times an odd, 100% it's going to be zero. What you have to check is something like an odd times an odd makes an odd function, but you could still get this inner product to be zero, and even times even, you'd still get them to be zero. We'll construct them. We'll come up with a method that guarantees that the polynomials that we construct are orthogonal, and we'll show that they are just the Legendre polynomials. Okay, good. But more important than that is I really think that picturing this inner product as kind of analogous to 2D linear algebra is really helpful, because quantum mechanics is all about doing inner products, right? Do you use the bracket? Bracket is just a notation for inner products. Another thing I could say just quickly is, what if in your wave functions, when you do calculations in quantum mechanics, you do crap like this, right? Conjugate. Why is it a conjugate? Okay, so okay, that's a good question. A dot B is the length. Well, let's make it easier. Let's do A dotted with itself. It's just the square of its length, right? What about a complex number times a complex number? If you want the magnitude of a complex number, you have to multiply it by its conjugate. That's why when you do inner products for complex functions, one of them has to be the conjugate. Because what you're doing when you calculate this is you're asking, like, what is the magnitude of this complex function? Well, it's the real part squared plus the imaginary part squared, which you multiply this. Okay. The other thing, so this is just a fancy notation if we're in 1D. So we have a conjugate dx. Okay, so that's why if you want this thing to be dimensionless, what is the dimensions? What are the units of your wave function? What are the units of dx? Meters, okay? So then what does this product have to have for units? 1 over meters. So that means each of these has units of square root of meters, right? So all of the stuff that we just talked about, like quantum mechanics is built on it. And so you should have this kind of algebraic picture in mind, I think, when you're doing those types of problems. All right, good. See you later.
For the sheet.
Yeah.